Yeah, so everybody can see this? There, can everybody see the screen?
Yes, sir.
Okay, so that's as we studied in the last class, the standard normal distribution. That is, if you take any normally distributed random variable, subtract from its mean and divide by the standard deviation, you get a standard normal curve, which is basically, and we said that the cutoffs for that are determined, right? So for example, 90% of the distribution will lie between minus 1.65 plus 1.65 and so on, right? So this is where we were looking at it yesterday, right? So if you write to find, so for example, if you want to find a quantile for the normal distribution, the value z, such that the probability that the random variable took a value less than z was 0.95. So you wanted to find a value such that 95% of the distribution is to the left of that value, right? Then in R, the command will be like this, q norm 0.95, right? Okay, so if you can actually draw this, right? So 95% distribution to the left of this point. Yeah, and this point on the x-axis is called, it will be given to you as by q norm. Yeah, so if you type in R q norm 0.95, see what you get. Q norm 0.95. See what you get. You should get the answer 1.644854. If you round it off, it will be 1.65. So it means that 1.65 is a value here such that 95% distribution is to the left of this value, right? It is called 95% quantile. Yeah? Getting this? Okay? Right, so we come down below. So we know, okay. So we also looked at yesterday that if you have a standard normal variable, right, if you have data which comes from the standard normal distribution, and if you take a sample of size n, then the sample mean is normally distributed, right, with mean mu, population mean, and variance sigma square upon n. Yeah, everyone understands why the variance is sigma square upon n? Because larger the data size, more accurate is your estimator. Right? Okay? Sure. So therefore, it must be true that x bar minus mu by sigma by root n is a standard normal variable. But I can simply rewrite that, multiply both sides by root n, and I will get this. Yeah? Root n into x bar minus mu upon sigma x will be a standard normal variable. Right? Okay. So, okay. So, therefore, we know that the values of root n x bar minus mu upon sigma x will lie between minus 1.96 and plus 1.96 with 95% probability. Because it's a standard normal. The area, 95% area of the standard normal is between minus 1.96 plus 1.96, right? Root n into x bar minus mu by sigma x is a standard normal. So therefore it will lie between minus 1.96 plus 1.96 with 95% probability. Yeah? Sure? So what you can write, when you write it like this, okay, once you write this, so here we have, right? Okay, and these are called critical regions, that also we have seen, right? Okay. So now we have to take a hypothesis, right? Suppose you have a sample, this is the sample. So enter this sample into your R now. How will you enter this sample into R? C. Right? So if you really have R studio, right? So you basically do 24 plus 32 plus 18, etc., etc., and calculate the sample mean, right? Our null hypothesis is that the sample comes from a population with mean 24, right? So if the null hypothesis were true, form this. And then form the z statistics, right? Root n into x bar minus mu upon sigma x. N is 14, so root n into x bar is 22.1429 minus the null hypothesis 24 upon 2, which is minus 3.4743. Yeah? Right? And are you getting the value of z statistic minus 3.4743? Yeah? Hello? Got this? Yeah? I want everybody to get this. We'll go and we're going to see some very important points today.
We are not getting the mean, we are getting the value of some.
No, but can you calculate the mean? How do you calculate the mean in R?
Mean x.
Yeah, so if you do this, let me open R Studio. Okay. Okay. So what is the, can you dictate to me the values of x?
24, 32,
Hold on. X is equal to C, 24,
32,
yeah, 18, 20,
19,
19,
15,
15,
22,
22,
24,
24,
25,
25,
20,
20,
27,
27,
19,
19,
17,
17,
28,
28. Right? So this is x. Okay? And if I now calculated 22.14, right? So are you getting this now? Yeah? So once you get that 22.14, right, then form the Z statistic. Root n into x bar minus mu. The mu is the null hypothesis. What is the null hypothesis? That the populations come from a mean of 24. And what is the alternative? That it does not come from a mean of 24. Right? Sure? So if you do root n, what do you get? So root 14 into 22.1429 minus 24 upon 2, right? And what is 2? 2 is the known, is the standard deviation. Variance is 4. So the standard deviation is the square root of the variance. 2, right? Okay? Right? And you get a value minus 3.4743. Right? Now, the question is, you can ask two questions. One is you can predetermine the level of significance. That you can say, okay, at 5% level of significance, the cutoffs are minus 1.96 plus 1.96. So if whenever my test value lies in is less than minus 1.96 plus 1.96, I will reject the null. Or alternatively, you can ask a question, what is the probability of type 1 error if I reject the null at this value? Right, which is called the p-value. Right? So you can ask two questions. One is you can say, okay, I will first determine what is the level of type 1 error that I am going to allow. So if you say 5%, then you will look at critical values minus 1.96 plus 1.96, because 2.5% of the area lies to the left of minus 1.96. 2.5% of the area lies to the right of 1.96, right? So 2.5% plus 2.5%, 5%. And then you will reject the null hypothesis. But suppose I now ask you a question. You got this value of the test statistic. If I reject the null hypothesis now, what is the maximum probability of type 1 error? Right, so what you will do? Minus 3.16 here, plus 3.16 here, and area to the left of minus 1.36, area to the right of plus 1.36. Right? Okay, 1.47 that is. So you can ask that question. So P norm 3.4743 will tell you what? Area to the left of minus 3. Area to the left of 3.47, right? If you take P norm, like what we saw, right? You please block threads. No, okay, but don't worry, right? Okay. So P norm 3.4743 will give you the value on the x-axis such that the area to the left of that value is what? Yeah? Sure? So the area to the right will be what is the critical value, right? What is the critical region? So 1 minus P norm will give you the area to that right. And because we are looking at the area to the right and the area to the left, you must multiply by 2. Right? Sure? So if you do this, what is the value that you get? So do this, no? 2 into 1 minus P norm 3.4743. So 0.0005118, right? So that's the maximum probability of going wrong if you reject the null hypothesis. And you see that probability is quite small. See, why is this important? Because previously we did not have access to computers. So you needed to predetermine these values. 5%, what is the cutoff for 5%, what's the cutoff for 1%. But really, and so therefore the computer told you previous statistical reasoning was okay. 5% critical value is minus 1.96 plus 1.96, so you reject the null hypothesis if the test value falls to the left and right. But there is actually a problem in that. Because whether to reject the null hypothesis or not is not the statistician's call. It is the call of the person who has to make that decision. Right? The statistician is nobody to tell a person whether to reject a null hypothesis or not reject the null hypothesis, because ultimately it depends on what are the costs and benefits of rejecting it wrongly versus not rejecting it. Right? So therefore the decision has to be left to the decision maker. And that's why p-value is what tells you. The only thing that as a statistician you can tell a person is, look here, this is the null hypothesis, this is the data. If you reject the null hypothesis, that's the maximum probability of going wrong. Then the call has to be taken by the person who is rejecting or not rejecting it. Because that entirely depends upon what are the consequences of failing to reject a null hypothesis. Yeah? Suppose the consequences of rejecting a null hypothesis wrongly are going to be pretty small, but not rejecting it are going to be very high. For example, in the older days of COVID, when there was no vaccination, nothing, we were all scared. If a person sneezed, right, you find somebody was coughing a lot in a bus stop, in a crowded bus stop, right, and sneezing and coughing and had a fear. Right, suppose your null hypothesis was that this person is healthy, right, okay, but the chance of actually rejecting that null, so even if you rejected that null hypothesis wrongly, even if you removed that person to a health camp, the cost wasn't much. But if you actually left that person, if you failed to reject the null hypothesis, even the null hypothesis is not right, when the person was actually infected with COVID, the cost would have been very high. Right, so those costs have to be made by the decision maker. Right now, if you find somebody coughing and sneezing in a crowded train, you won't really get that poor person, tie that poor person up and send him somewhere to a health camp, because now those costs and consequences have changed. Right? So the decisions ultimately have to be made by the decision maker. Right? So I'm now going to ask you a question. Right? Suppose now, suppose now I have the data, right? Suppose X is the following data. Okay? Yeah? You have to tell me what is the maximum probability of type 1 error if you reject this null hypothesis. What is the probability, maximum probability of type 1 error, which is the p-value. So what is the first thing that you do? Calculate the z value, right? Okay. First, calculate the z stat, right? Which is what? Root n into x bar minus mu upon sigma. Sigma is known to you. Mu is your null hypothesis. x bar is the what you get from the data, root n. Yeah? Calculate that. Then you have to calculate the p norm. And 2 into 1 minus p norm will give you the maximum probability of type 1 error in this case. So that is the p value. P value and level of significance are different, okay? आज वेटिंगमध्ये कसं कोण नाही, सगळे वेळेत आले तर. कळलं आलं? सो व्हॉट इज एक्स बार? सो एक्स बार is mean of x, right? Yeah, so let's see what is x bar. Yeah, x bar, right? So z is equal to square root of length x, yeah, root n. Length x will give you n, right? X bar minus 75 divided by square root of the variance 3, right? So what is z? Minus 65 point, right? Sure? Yeah? Okay? Right? And then say p value is equal to 2 into 1 minus p norm z, right? And what is p value? It can't be, right? So what is z? Z was, so I'm sorry, what was the z value? Hey.
So this 3, is it divided by the whole or just with the n minus 7?
Pardon?
This 3 variance, is it divided by the whole or just with x bar minus 7?
No, see, x bar minus mu by sigma by root n. Okay, so if you look at this, what have we done? So your formula is this, it, no? Why? Because the formula is x bar minus mu by sigma by root n, right?
Shouldn't we divide it the whole by 3? Like back in R. We have divided
Okay.
it just with x bar minus.
सर तुम्ही तो x अरे कॅपिटल x घेतलाय छोटा x
लेट मी सी. मग काय करूया म्हणतो इथे, सो लेंथ स्क्वेअर रूट ऑफ
नाही तो x मोठा पाहिजे capital. तुम्ही अरे
ओ सॉरी या, अच्छा माझं इथे कॅप झालंय, हां, राईट. सो व्हॉट इज झेड? minus 24 point. Yeah? Right? Thank you. And now area to my, आता प्रॉब्लेम काय आहे कि area 2 येणार नाही कारण area to the left of minus 24, right? So we just have to calculate the area to the left of the test statistic and multiply by 2. In this case, it will not be 1 minus p norm. You do it 1 minus p norm if the z value is positive, because then you will calculate the area to the left, right? Area to the, if you have to calculate the area to the right of a positive number, then you have to calculate 1 minus the area to the left of that number. Our value is a negative number, right? So what we have to do is only p norm into 2. So it has to be only this, right? Oh, it's a very small number, right? E raised to minus 136, so 0.00000000. Are you getting this number? Because minus 2.4, minus 24 will be really to the left, no? For a normal distribution, the area to the left of z, right, is given by it's a very small number, right? 2.442267 e raised to minus 136. So decimal point has to move 136 to the left. So it is 0.135 zeros and then 136. It's a very small number. Yeah? And if you multiply it by 2, then that becomes 4 point something. So it's still a very, 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 very small number. Yeah? And that is the maximum probability of type 1 error if you reject the null hypothesis, almost a non-existent p-value. Right? Okay, now, suppose I change the null hypothesis, okay? Suppose I change the null hypothesis from 75 to, so what is this number? X bar is, so I change this number from 75 to say 55. Yeah? If I change this number to 75 to 55, then tell me what happens. The p-values become bigger, right? Sure? And if I change this number to 54, so if I change number to 53, the p-value is very big, so you will not reject the null hypothesis here. Yeah? There is 61. So what is happening? If I get mu closer and closer to x bar, the probability of type 1 error rejecting the null hypothesis increases. What does that mean? Can you kind of say something about it? What does it intuitively mean? So when mu gets closer and closer to x bar, the probability of type 1 error increases, right? The probability of rejecting the null wrongly increases as the hypothesis gets closer and closer to the actual mean. What does that mean? What does intuitively इसका interpretation कैसे?
The sample is too representative of population.
Yeah, but can you kind of make it more intuitive? See, look at this test statistic, okay? Look at this test statistic, right? Look at this, right? What is x bar? What is mu? Is the hypothetical population mean. Hypothetical. अपना दिमाग में है ना? X bar is what? It is a evidence. Right? So x bar minus mu is what? It is the gap between the evidence and the hypothesis. Right? What is n? N is our information. So what is this telling you? This tells you that the z statistic will be larger if n is larger, because n is the numerator. It means that if you have more data, you are more likely to be able to reject a null hypothesis, which is not true, because you've got more observations now. Yeah? Does Vadeshwar sell a good... Yeah, pardon?
Can you repeat this?
Yeah, so basically x bar... Yeah, I am doing that. So x bar minus mu, x bar is the evidence, mu is the hypothesis. X bar minus mu is the gap between the evidence and the hypothesis. Right? N is the number of data points that you have, number of information. Now from mathematically it means that if n is larger, the z statistic will also be larger because n is in the numerator. Right? Okay, what does it mean? It means that larger the n, more likely you are to reject a null hypothesis and the probability of type 1 error will be smaller. Right, what is probability of type 1 error? Failing to reject a null, rejecting a null wrongly. Right? Okay, now let me kind of give a concrete example. Right? Okay, suppose there is a very famous restaurant here. I don't like it at all, but a lot of people like it. Right? There is a South Indian restaurant called Vadeshwar. You find branches all over the city, right? Okay, okay. Now suppose somebody tells you that the dosa in Vadeshwar is wonderful. So my null hypothesis that dosa in Vadeshwar is great. And I go there once, so that's my hypothesis. If I go there once and eat it, I don't like it so much, the evidence is that I didn't like the dosa so much. Right? Evidence is there, hypothesis in my mind. Right? The gap between the evidence and the hypothesis is large. But my friend might say, no, today there's a by chance, sometimes it happens, but if you eat this dosa regularly. So I go the second time also. And second time I find it equally bad. And if I keep on doing this again and again and again and again, I keep on finding that the quality is not improving. Then the more often I visit, the stronger will be my confidence in saying that the dosa in Vadeshwar is not good. The null hypothesis that the dosa in Vadeshwar is great. Alternatively, it is not good. Right? The null hypothesis is not true. N is the number of times I've eaten the dosa. X bar is the actual dosa that I eat. Right? The actual quality of the dosa, that is the evidence. Mu is the hypothesis that the dosa is great. Right? And I don't like the dosa so much once I went. But if I go on repeatedly doing that and repeatedly I find that the dosa is not good. Right? Okay, then the null hypothesis, so I have a greater chance, right, of rejecting the null hypothesis. But for that remember the very important point is that the dosa I eat on each time should be slightly different from the previous time's dosa. Right? For example, I can't use this hypothesis to say Dilwale Dulhaniya Le Jayenge is a great movie, and then I watch it once, I don't like it again so much. How many times I watch it, I'll be watching the same movie, no? So there'll be no evidence coming in. That is where N plays a role. Every time I see the movie again and again and again, so that doesn't hold for movies, but that will hold for dosa, because the idea is that it's not the same dosa every time. There is a little bit of variation here and there. And that's why I want to watch it more, eat it more and more and more often. And ultimately I've eaten it, the longer I eat it, the greater is my confidence in saying that the dosa is horrible. Right? The dosa is not great. I've eaten it so many times, right? Okay? Sure, that's the whole idea. The sigma x part is important because sigma x part takes away the units of, right? That's a unit free thing. So my evaluation of the dosa might be in some other units, your evaluation of the dosa quality might be in some other units, but that won't matter. Yeah? Is this clear? So x minus mu, x bar is the evidence, mu is the hypothesis. X bar minus mu is the gap between the evidence and the hypothesis. Now when my mu was 75 and x bar was 52, the gap was large. And so if I rejected an hypothesis, the error was not likely to be very high. But as I kept on increasing mu and getting it closer and closer to the evidence, so actually the evidence was not so far away from my hypothesis. then the probability of type 1 error kept on increasing. Yeah? You see this point? Sure? Clear? So basically, larger the gap between the evidence and the hypothesis, larger the sample size, and lower is the variance of the population. Right? When does the lower the variance of the population come in? So if the dosa that I ate, the quality was highly variable, suppose. So every time, sometimes the dosa is great, sometimes it's horrible. I am saying that by and large it's good dosa, right? That's a null hypothesis. Right? If the quality is variable, then if I eat it just 3 times, I can't reject the null that the dosa is not good. But the variability of the dosa quality was not very great. Very little. Dosa would do 19-20 thoda idhar udhar hota hai, right? Then it's easier for me to reject the null hypothesis just by eating it only a few times. Right? Is this clear? Sure?
I have one question.
Yes, Pallavi.
So why do you multiply that formula by 2? Like, so I understand that, if you're going for a one-tailed test, then we're looking at one side of the distribution.
No, we are looking at actually a two-tailed test, Pallavi. Because the reason I am doing this is because, you see, what does P norm tell me? Okay. P norm just gives me, so this is what P norm will do. P norm will give me the area to the left of this curve. Okay, I want this area plus this side area also, no? What do I want? I want something, I want basically, I want this area plus this area, right? P norm will only give me this area if the number is positive. So I must find this area first, which is 1 minus P norm, and multiply it by twice to get this plus this area, right?
So can you go back to that art studio or that book
Yeah.
course?
Yeah, here.
Sir, it is like P norm this, sir. Why there is no 1 minus?
It is not 1 minus because the reason, because Pallavi, what is the value of Z? Z is negative in this case, right? It is minus 0.50, correct? So to get minus 5.50, what do I have? Minus 5.50 will be, I already have this to the left, right? So I don't have to do 1 minus, correct?
Sir, I am getting a 0 actually. I don't know. Like,
No, check your calculation. Yeah. Okay, so now the next important point, right? Kaga, something I can help? No. Okay, so basically, now the important point is, remember, the larger the n, the greater is going to be the z value. So larger the n, more likely you are to reject the null hypothesis. Right? So look at the role of evidence in hypothesis testing. More evidence, more data will lead to greater chance of falsifying a null hypothesis which is not true. But you can never prove a null hypothesis with more data. In the real world, you can prove a null hypothesis with more data, right? I can go to Adeshwar and keep on eating the dosa again and again, and the more I eat it, the more I like it, and I say it's great dosa. In statistical hypothesis testing, I can't do that. Right? More evidence is tailored to reject the null hypothesis. If I keep on increasing sample size so large that Z will become large, sufficiently large. So any null hypothesis can be rejected by a sufficiently large sample size. right? You can reject any null hypothesis with a sufficiently large sample size. Yeah? You can reject any null hypothesis with a sufficiently large sample size. Right? Sure? Okay? And that's going to be an important point. Right? Why is that the case? Why is that the case? Because you must go to the philosophical roots of the whole hypothesis testing idea. This goes back to sometimes in 1920s. Right? There's a politics of it, right? There is a scientist, a philosopher of science called Karl Popper. Have you heard his name? He wrote a very famous book called The Logic of Scientific Discovery. What was Popper's point? At that time, the Soviet Union had just been established. Marxism as a philosophy of world history was becoming very important. And what was the Marxist idea at that time? The Marxist idea at that time was there is a certain progression of history, no? Slavery to feudalism to capitalism, which will eventually lead to the rule of the proletariat. Right? Popper said that this is not a scientific statement. It is not a scientific statement because Popper said that a statement to be scientific, it has to be capable of being falsified, in principle at least. So 2 plus 2 is equal to 4 is a correct statement. But it's not a scientific statement, but you can't falsify it. Right? Whereas, if I drop my specs from here on the ground, they will break. Is a scientific statement which can actually be tested by dropping them. Right? I hold it like this, I drop it. If it doesn't break, I hold my null hypothesis, I drop it again, doesn't break, I keep on holding my null hypothesis, I drop it, I hold it again, I keep on dropping my null hypothesis, I keep on doing this, till eventually if sometimes it breaks, I say my null hypothesis is not correct. So a scientific statement is only a statement which you hold provisionally, given that it has still not been proven false. Yeah, that is the Popperian idea of science. So you have a certain scientific hypothesis, so you have a certain scientific theory, say evolution. And then you find evidence which doesn't match up with evolution, so you reject evolution. That was the Popperian idea. So therefore evidence can only be used for falsifying. Yeah? Evidence cannot be used for validating a null hypothesis. In fact, a null hypothesis which is true is not even testable, will never be rejected. Why? Because if the population mean is 22 something, what is sample mean here? 54 something, right? If I put mu as the same value, what will be that z statistic? 0, which will never be rejected. Whatever my n, whatever my sigma, it will never be rejected, right? So a true value, true hypothesis value will never be rejected. Whereas a hypothesis which is not true can always be rejected provided your sample size is sufficiently large, right? Can you guys hear me? Sorry, there was certain, I think one of the switches on which I had connected the laptop wasn't working. So I didn't get that, right? Okay, so basic idea is कि the null hypothesis, any statistical testing idea is the evidence minus the hypothesis, the gap between the evidence and the hypothesis divided by the standard deviation. That's because we want to remove the effect of the units and multiplied by the sample size. The idea is that greater sample size is used to falsify a null hypothesis. Whereas in the real world, you might want to get more sample size to even validate a null hypothesis. Right? I might start with a null hypothesis that this person is very trustworthy in an economic interaction. Right? And then he works with me, I keep on finding that this person is actually trustworthy. Right? Okay, so there is really, I can validate my beliefs. I can validate my hypothesis with the real world data. But because statistical hypothesis testing is designed in such a way, right, that greater evidence can only falsify a null hypothesis. And the point, yeah.
So can we say when we have more and more evidence, the probability of our hypothesis being wrong increases?
No, if you have more and more evidence, the probability with which you will fail to reject a wrong null hypothesis will drop. The p-values will drop, right? Whereas it says that if your null hypothesis is actually correct, if x bar is the same as mu, then you will never reject that null hypothesis. Right? So the point is, whatever data you have, even if you don't have any data, if your null hypothesis is just what you have seen, right? If your alternative, if your evidence and the null hypothesis are the same, then you don't need any more data, because more data is not going to change anything. X bar minus p is going to be 0. So whatever n you use, that number is not going to change, right? But if you are not sure about your null hypothesis, then as the sample size increases, the probability with which you will fail to reject the wrong null hypothesis will drop. Understand? Sure? So point is, if you have a large enough sample size, you can reject almost any null hypothesis. And sometimes it's meaningless, right? For example, the null hypothesis is that the population mean in Pune is 51.2. And my sample says it's 51. Shouldn't really make a difference too much, right? But if you keep on increasing a large sample size, you still reject that null hypothesis. Right? Sure? So I typically work with very large data sets. Right? My data sets generally go into lakhs of observations. So there is no null hypothesis that I ever fail to reject. And so it doesn't make any sense to me, because I know that this, whatever null hypothesis I put in, I don't fail to reject it. So it doesn't tell me much information, no? My whole statistical tracing exercise doesn't tell me much, because any null hypothesis I'm going to use is going to be rejected. Yeah, unless by chance I hit on the correct null hypothesis to start with, which is going to be very difficult. Yeah? So for instance, you have a sample size of 2 lakh people in Pune. You are trying to calculate the per capita income in Pune. And the per capita income in Pune is, suppose on the sample size you get, it's 5,632. And your testing null hypothesis is 5,630, you will reject the null hypothesis unless you exactly your sample size, sample mean and that match exactly. So that's a problem with hypothesis testing, which I just wanted to kind of make you aware of. Right? So increasingly we are becoming a little less satisfied with these ideas of p-values and other things. Right? Okay? And also I'll tell you why we can actually fish for p-values. So we can actually do our statistics in a way which kind of gives us the p-values that we want. Right? Because the whole idea becomes rejecting a null hypothesis. No? You see, there is a huge problem in that, because typically what happens, you start with a null hypothesis. Most scientific papers will accept your paper only if you reject some null hypothesis. There is a significant p-value. If you don't have a significant p-value, journal is going to say no, right? So typically many interesting hypotheses, because you don't, their p-values are not small, you can't reject, go into the drawer because you don't write a paper on them. So the hypotheses themselves could be very interesting, but your data failed to reject those hypotheses, and which is actually a very good thing, right? But the p-values are not significant. And because your p-value is not significant, journals don't publish your paper, right? This is called this is a name to this problem in scientific research. Its name is filing drawer problem. It's got a name. It's got the filing drawer, I think cabinet files problem or something, filing drawer problem or something of that kind, right? Where just because you don't get significant p-value, you stop that research. Your papers don't get published. So interesting ideas nobody uses those interesting ideas even when they're actually fitting in with the data. Yeah? The solution about is not to only think about p-values, but to think of wider things, right? Okay, and not necessarily econometric. You should be able to tell a story with your data anyways. Very similar is the problem of difference between causation and correlation. With this whole industry in economics which says that a hypothesis is interesting only if it's a causal hypothesis. But many times you can't do that, right? So many times there are many interesting stories which actually can't be fit like this. That X impacts Y, but Y does not impact X. Right? In fact, there is a lady called Ang Yang. That book you must read. This book is about China essentially, how China escaped the poverty trap. But Professor Yang, what she's doing is she is now looking at what she calls complexity theory. So in complexity theory, there are necessarily feedbacks between variables. So X impacts Y and Y also impacts X. Right? She says that economic system are not like toasters, no? You put in a plug, you put in a bread, and you press a button and the bread comes out. Right? Economic life is much more complex. Right? Various parts of the toaster adopt to one another. They adopt in ways, for example, cities don't grow like this. Right? Cities grow in a very complex, interdependent fashion. Right? There are events which nobody could have forecasted before, anticipated before. Right? There is a very open-endedness in economic processes. So she is looking at what are called complexity dynamics. And if you go to her website, there are one or two very interesting and simple papers to understand. Right? So which is because this causation becomes there are very few things in economic life in the real world which are so easy to establish causation. So they look at natural experiments and those kinds of things, right? Where you desperately try to look at other things being the same and one thing affecting another. But you miss out on a lot of very important things happening around you because you don't have a story to tell which will fit in a journal's way of causation and publish a paper, right? Okay, so you have to look at slightly wider kind of things. Yeah. Okay. So I hope everybody understands what a basic hypothesis testing idea is. Okay. So now, so we were here, right? We did this. Yeah. So and you can have a copy of this book. This is my old 2010 book on econometrics, which I claim is very simple to read.
PDF
Patholi, na? Everyone's got that PDF, right? For a long time, Sage didn't allow for a PDF, but now it's out of print, they're allowing us to make PDFs. Okay, right. Huh? Oh, screen share hot nahi hai? Okay, now I'll share the screen, yeah. Yeah, so going to this, right? Okay. So now, interestingly, what we do is calculate the power of a test. Okay, now what we're going to explore is, suppose the null hypothesis is not true. Okay? Suppose the null hypothesis is not true. So what we're going to do is, basically, suppose we are going to generate data where the value of mu is -3. We know that, right? The population mean is 3. Right? Okay. And the variance equals 1. So standard deviation is 1. So data is normally distributed with actual mean equal to -3 and the standard deviation is 1. Right? Then we take a null hypothesis take a test of hypothesis for the null mu is equal to 0 against mu is not equal to 0. Right? But what do? We do it 300 times. We do this test 300 times. Right, so 300 times we take a sample of size whatever from the data, we take a Z test and we calculate right. Then sometimes it will reject the null hypothesis, sometimes it will not reject the null hypothesis. The null hypothesis is mu is equal to, the real value of mu is -3. We'll start with some value of mu, which is not equal to -3, some fixed value. Right? From that data, take a sample of some size and take a z-test with with mu is not equal to say -3, mu is equal to some other value. So we'll take a false null hypothesis, right? We'll fix that null hypothesis and we'll do this 300 times, right? Okay, when you do it 300 times, because there is some probability of type 1 error and type 2 error failing to reject a null when the null is not true. In some fraction of the 300 times, the null hypothesis will be rejected, some fraction will not be rejected. Let's try to find out what is that fraction, and then see whether that fraction depends upon the sample size, how close is the null hypothesis, and so on. Right. So what we'll do is, in the first stage, right, in the second stage, we'll increase the value of mu by a small amount, right? So value of mu will go from -3 to -2.98, etc., etc., and then repeat the step again, right? So give you the probability of type 2 of mu is equal to -2.98, and we'll keep on changing the value from -3 to +3, right? The fraction of time. So the point is that if you do this 100 times, and the fraction of times you reject a null hypothesis is not correct, it's called the power of the test, right? So if you do this many times, and the fraction of times you reject a null hypothesis which is not correct, is called the power of the test, right? So we're going to look at the power of the test as the data goes from -3 to 3, right? Okay. Which is called the power function, right? So we're going to calculate the power function of the data, right? And so there is a code here that I've written. So first, n is 50, right? Okay. Sample size is 50. That is going to be sample size. How many times you're going to take the sample? 300 times. Yeah? So rem, first we create a column of 300 zeros to store all the 300 values. Yeah? Okay? Then what do we do? Mu is equal to -3, sets the initial values of mu, right? I is equal to 1, repeat, P mu is 1 minus P norm, 3 is our null hypothesis, is basically the sample mean, right? Assuming that mu is the sample mean, right? Assuming that the mu is a sample. We are not currently taking a sample, right? Mu is the sample mean, right? Minus squared n into mu, P norm, right? Minus P norm 3 squared, generates the Z test and measures the value, right? So basically, if you can do it later. If you do this, what you see is here. So basically the true value of mu is 0, right? As you keep on moving away from the true value of mu, as the assumed sample size, population sample mean gets different from 0, the probability of type 1 error, you see, you start to get a bigger and bigger type 1 error, type 2 error, right? So basically, we can see that the power of the test is pretty low for values of mu close to but not equal to 0, right? Okay. So now I'm going to show you one more picture. If you increase the sample size, so let's do that exercise now, some hands-on exercise. So we'll get to learn this, right? Okay, or at the moment this might be a little confusing, so leave it aside. We will come to this point again. All right. Okay. Now you guys are familiar with, I think that power computations will take a little bit of coding in R before we go there, right? So we'll come back to that. But the basic idea of the power of a test is clear to everybody. Greater the sample size, greater is the chance of rejecting a null hypothesis, right? Which is not true, right? Okay? Sure. In the vicinity of the true null, you are less likely to reject a null hypothesis. Right, so that if the true value is 50 and your sample, you're testing whether x bar is 51.2 or something, you are less likely to reject a null hypothesis. But otherwise, as you keep on going away, you are more likely to reject a null hypothesis, right? Which is not true, right? So power of the, so important thing you should know is that the power of any test depends upon the sample size and the population variance. Larger the population variance, you might need a bigger sample size to reject a null hypothesis.
असं graphically थोडं डोक्यात येते.
Huh.
We have a population mean.
Right.
Right.
Huh.
आणि असं आपलं नॉर्मल फंक्शन आहे. सो इफ वी इन्क्रीज द सॅम्पल साईज ते जवळजवळ येत जातं आपलं कॉन्फिडन्स इंटरवल आणि मग आपला
हां.
हायपोथेसिस बरोबर असायला आपला मीन एकदम जवळ असलं म्हणजे थोडं जरी इकडे तिकडे असला सॅम्पल
करेक्ट. त्या ग्राफमध्ये तसंच दिसतं ते, फक्त वी स्टील हॅव नॉट गॉट टू दॅट पॉईंट ऑफ डुईंग दॅट कोडिंग, सो आय विल राईट. So we now know what is,
One question.
yeah. Yeah, Pallavi.
Yeah. So, sir, my question is, like, sir, how to like make use of like this type 1 and type 2 error together?
You can't make the use of them together, right, Pallavi? You can't make use of type 1 and type 2 error together because they are addressing different questions, right? A type 2 error, type 1 is only telling you what is the probability of rejecting a null wrongly. Right? Whereas type 2 is telling you what is the probability that you will fail to reject a true null. You want the probability of type 2 error to be as small as possible, or the power of a test statistic to be as large as possible, because power of the test statistic is nothing but 1 minus the probability of type 2 error. Whereas for type 1 error you can't say that. Type 1 error really is the maximum probability that you are going to allow of rejecting a null hypothesis wrongly. And that depends entirely on the costs and consequences of the wrong decisions. So type 2 error you want always to be as small as possible. But type 1
The test is simply 1 minus the
probability of type 2, power of a test is 1 minus the probability of type 2 error. Type 2 error is failing to reject a wrong null. Yeah?
Okay, so we can automatically get the power of the test, right? And we can simply like calculate the power.
You can simply calculate the power. The power depends positively on n. Larger the n, greater is the power for any x bar minus mu, and larger the variance of the population, smaller is the power. Right? The population is highly variable, then less. Right? Okay. So now, okay, let's now come to other kinds of, I am at the moment not going to say to type 1, type 2 because that you can read from this text. It's really very easy, right? We also can create confidence intervals. Very easy idea. So we know that root n x bar minus mu by sigma x is a standard normal, will lie between minus 1.96 plus 1.96. So all that I do is multiply both sides by sigma x upon root n. Right? Minus 1.96 plus 1.96. So basically it says x bar will lie between minus 1.96 into sigma x upon root n on one side and 1.96 into sigma x by root n on the other side. So there is a 95% chance that x bar will lie in these two intervals. Right? So if you take a population, right? Okay, and if you take, say, a very large number of samples, right, then 95% of the times mu, the true population mean, will lie between this interval and this interval. Right, so every time you take a sample, you calculate x bar. You know what is n, right? You know what is the population variance. So for each sample, each x bar, you will get a confidence interval. So if you take 1,000 such confidence intervals, then the data, this theory says that 95% of those confidence intervals will actually contain the true mean. Right? Sure? That is why they are called 95% confidence intervals. If you wanted to change this number from minus 1.96 to minus 1.65 and plus 1.65, then you will get the 90% confidence intervals. Yeah? Sure? Again you see, larger the n, the narrower are the confidence intervals. Because sigma by root n will keep on becoming smaller and smaller and smaller. Larger the sigma, the wider are the confidence intervals. right? So it just means that your precision of your estimate becomes more and more precise with larger n, becomes less and less precise with larger population variance. Right? So the two deciding criteria are really what is the population variance and what is the sample size. Yeah? Very often you can't do much about population variance, but you can do things to the sample size, and very soon we'll see. Of course, everything here is assuming that the data are normally distributed. And we'll quickly come to what happens if the data are not normally distributed, right? Okay. So that's how you create confidence intervals, right? Okay. So for example, if you have this data, right, 23, 22, etc., etc., construct a 95% confidence interval and a 90% confidence interval. How do you construct a 95% confidence interval? You know that a 95% confidence interval will be such that p minus 1.96 into this, okay, is less than or equal. So basically p minus 1.96, p plus 1.96, right? So x bar will lie between, sorry, this p should have been outside. That's a typing error from Sage, right? So probability that root n x bar minus mu by sigma lies between minus 1.96 plus 1.96 is 0.95. So basically you have to calculate x bar, right? Okay? And then you have to kind of get this, so x bar minus 1.96 into 2 by 12, because sample size is root n, sigma is given as 2, x bar minus 1.96 into sigma by root n, x bar plus 1.96 by sigma by root n, so you get 27.45 and 29.71, so that's a 95% confidence interval for the population mean, right? So if you take 1000 samples, 990 if you're taking whatever 95% of those, 950 of those will really lie between, the population mean will lie between these two values, right? Will contain the population mean. 90% के लिए this number changes from minus 1.64 to plus 1.64. P is the probability that root n minus x bar upon mu by sigma x lies between minus 1.96 plus 1.6 is equal to 0.90. हे p ते बाहेर पाहिजे, ते सेजवाल्याने टायपिंग मिस्टेक केला आहे, p इथे काढला आहे. That's a typo in that book. ब्रॅकेटच्या बाहेर पाहिजे. Which is probability that the standard normal lies between minus 1.96 plus 1.96 is 0.95. The probability आहे खरं. Right? Okay. Now we come to a very important idea, right? So what is the idea? Now we require the data to be normally distributed. But how do you know that the data are normally distributed? कोणी सांगितलंय? मग नसेल तर ते सगळं ते लॉ ऑफ ते सगळं जाणार ना, म्हणजे एक्स बार वी सॉ दॅट द पॉप्युलेशन हॅज टू बी नॉर्मली डिस्ट्रीब्युटेड विथ अ नोन मीन अँड अ नोन स्टँडर्ड डेविएशन अँड ओनली देन विल एक्स बार बी नॉर्मली डिस्ट्रीब्युटेड, so on and so forth. What is the population not normally distributed? You are doing a study of income levels, for example, in Pune. Income levels are not normally distributed, right? So that is where the central limit theorem comes to use, right? And what does the central limit theorem says? Okay, think of n such observations, right? x1, x2, x3, xn, right? So each observation that you're picking up, so if you have n data points, then you really have n different random variables. Like suppose you did a sample size of 1000 and the first person in that was Savita. But Savita could have been anybody, no, because chosen. So the first person you have chosen is a random variable. The second person you chose is a random variable. Third person you chosen is a random variable, right? Because the first observation could have been filled by any of those people, no? Second observation could have been the first observation that you've got is itself a chance outcome of a random experiment, right? Now assume that each of these random variables have the mean mu, right? So because we are looking at populations from the samples from the same population, right? Anybody in the population could have been chosen as the first person. So the mean of the first observation is the population mean. Anybody from the population could have been chosen as the second person. So the mean of the second person is also the population mean, right? So each one has a mean equal to the population mean, right? Okay. Right. Now, if you calculate the standard variable like this, right? So if you calculate a standard normal, right? X minus, so we calculate the sum, right? Let x be x1 plus x2 plus xn. If you add all these random variables together and calculate the sum, and then you calculate a statistic, which is the sum of all these random variables, capital X, which is x1 plus x2 plus xn, minus n times the population mean, divided by the square root of n times the standard deviation. Yeah? Then this number, the theorem says, will have a standard normal distribution with mean 0, standard deviation 1, as the sample size becomes larger and larger and larger. So as the sample size becomes larger, as n becomes larger and larger and larger, this Zn, its probability distribution will get closer and closer to the standard normal distribution. Right? So it says that if x1, x2, x3, xn are random variables, all of them have a mean mu. Whatever the distribution of x1, x2, x3, xn, and the standard deviation sigma x, if you sum all those x's, x1, x2, xn, etc., capital X, minus, and you calculate capital X minus n times mu, divided by square root of n times the standard deviation, the resultant, as the sample size becomes large, this Z will become, its distribution will get closer and closer to the standard normal. Right? Actually, interestingly, you see, first, right, if you divide everything by n, if you divide the numerator by n, right, if you divide each value numerator by n, what will you get? This will be summation x upon n minus n mu divided by n, so mu. So x bar minus mu will be in the numerator, right? What will be denominator? Sigma, because we are dividing by n, right? So the numerator here is root n into root sigma x. This is essentially root n into root sigma x. If you divide by n, root n will go. And what you will get is root of sigma x upon root n. So standard normal. Right? And as n becomes large, this will become closer and closer to the standard normal, right? That is called the central limit theorem. So you get this, right? So now let's do this. Right? Okay.
So I have one question here.
Yeah, Pallavi. Yeah.
So when you're talking about, like, let's say we take a sample size of 1,000.
Yeah.
So just when you said that, like, the mean of each of the observation is the population mean. So are we considering each of the observation as a sample of size 1?
Yes, because each of the observations is a sample of size 1, no?
Okay.
And then it says that if you actually take the sample mean of all these observations, subtract from it the population mean, and divide by the square root of sigma upon root n, right? What you will get is a z value, and as n becomes increasingly large, this value will get closer and closer to the standard normal, right? Okay, so if you really do it here, right? So I have taken a, right? Okay. So think of a distribution called a Poisson distribution, right? So I'll show you first how a Poisson distribution looks like, right? So I say x is equal to, right, R Poisson, so control plus plus plus, could I say plus plus plus, could I? No. प्लस कुठे आहे प्लस 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 हां ओके नाही खूप वाढलं ठीक आहे okay so our poise say I want 1000 numbers and to specify a value of lambda called say 3, right? So so this gives you Poisson distribution, and if I now just say plot x, right? Plot, density x, right? Plot, so first calculate the density of x and then plot the density of x, right? So you'll clearly see That's why I don't too much like our studio, because we got this painful thing about, yeah. Hey, okay, right? Sure? So this is the kind of a Poisson discrete random variable, right? Does it look normal or anything? No, right? If I increase the number of draws that I am doing, then probably it might look a little bit more continuous, but still a so it's not really a normal variable, right? It's not a, right, plot density x, yeah? Right, so Poisson distribution is not a normal distribution, right? So what I'm doing from here is, I'm now doing, so I'm taking some data from a Poisson distribution with mean equal to 0.002 and the variance also equal to 0.02. Right, so this is data, and then I'm calculating on a sample of size 10, right? Root n into x bar minus mu upon the square root of the standard deviation, because as you know in Poisson distribution, lambda starts for the mean and the standard deviation and the variance, right? Poisson distribution, so I get this Z10. Now you know this is data generated from a Poisson distribution. Now I'm going to increase the sample size to 100, right? Again the data is coming from the same Poisson distribution, right? And then I'm going to change it to 1000. So if you have it just as sample size 10, this is how the distribution looks like. If I change it to sample size 100, this is how the distribution looks like. And if I take it to sample size 1000, it is now becoming more and more and more and more normally distributed, right? And if I take a very large sample size, 500,000, it looks almost normal, right? Yeah? So the idea is that from whatever distribution the data comes in, as long as the sample size is sufficiently large, you can still calculate the sample mean minus the population mean upon sigma by root n and use a z distribution for it. But you need large samples, right? What to do with small samples, we'll deal with it now. We have to do simulations, we have to do permutations and other kinds of things, right? You really go what is called a Monte Carlo simulation and calculate p-values, that we'll do later. But basically currently the central limit theorem is this, that whatever population the data have come in, x bar minus mu upon sigma by root n will be standard normal as long as the data are sufficiently large and all the x1, x2, x3, xn are all independently and identically distributed. So all of them have the same mean, all of them have the same standard deviation, they have come from the same population basically, and they are independently chosen, right? So what is the first observation has nothing to do with what is the second observation. You don't go to a family and say where is the mother, wife, father first observation, mother second observation, third observation, brother-in-law, all that. You don't do that, right? You choose households independently. Sure, if you do that, this is a powerful theorem that is often used, and we then say that we can still use the Z statistic, right? So you can try this now, right? You can try this, okay? You can try writing this code and just play around and see whether you can actually, change the sample size to 50 first, then change this to 500, then change this to 5,000, and so on, and then say what you get. So basically, yeah.
For you to use Z statistic, we always assume that the population variance is known, which in real terms.
Then you use the t-test then, if you don't know the population variance, but we'll come to derive that.
But then the same activity is applicable for t-test.
Same. Right, so what Savita is asking is, we don't know the population mean, population variance, we are assuming that we know the population variance. If you don't know the population variance but replace it by the sample variance, then the distribution becomes the student's t distribution, right? But the same logic, everything holds. And I will show you how the student's t distribution will also get to the normality. Is the idea clear to everybody? Now just experiment with this. Write this code, right, and play around with this code a little bit. with the sample size, play around a little with the sample size and see whether you can actually reproduce these series of graphs, right, that I've got there up, and make sure that you can actually test out the central limit theorem. That's the beauty of the normal distribution, no? A lot of things in the real world follow that bell-shaped thing.
So, sir, when we actually say that in India there is an income inequality, to begin with, we are saying that there is no normal distribution.
No, but no, what we're saying is, all that you're saying is, if you take suppose income is unequal, you take a certain sample, you have a null hypothesis that the mean income is 50,000. You take a certain sample, you calculate the sample mean minus the population mean, create a Z statistic. Then all that it says that this Z statistic will be closer and closer to the standard normal as n becomes more and more. So you can still use the Z distribution to take hypothesis about an unknown population mean even when the original population is not normally distributed. Yeah? So just try this out and play around with this a little bit. And just try to see what happens if you, this is a sample size. Okay, I've used 5 lakhs, but start with 50, 500, 5,000, and see how you get closer and closer to normality. Okay, folks, so we looked at the Z distribution. We'll now look at the chi-square distribution. That's another important distribution that comes to, that is important for us, right? So, the chi-square distribution is essentially derived only from the standard normal, right? So, if Z1, Z2, Z3 are standard normal variables, so if Z1 is a standard normal variable, Z2 is a standard normal variable, Z3 is a standard normal variable. Think of making Z1 square. Think of making Z2 square. Think of making Z3 square. And adding all these. So if you take Z1 square plus Z2 square plus Z3 square, what the distribution that this sum follows is called a chi-square distribution with 3 degrees of freedom. So chi-square distribution is nothing but if you sum n independent standard normal squares and sum them, then the distribution followed by this sum is called the chi-square distribution. Right? So Z1 square, Z2 square, Z3 square, Z4 square, Z5 square, add up them will be chi-square with 5 degrees of freedom. Right? That is the definition of a chi-square. Right? Okay. Now, this is the very important theorem, right? What is the use of this chi-square? Statisticians will never think of an idea unless they can put it to use somewhere. Right? Statisticians are very instrumental people, right? They will always make use of something. Otherwise, they don't think of concepts. So, think of this, right? So, this theorem is very important. What does the theorem say? That suppose you have a sample. You have a sample of size n. Okay, listen to this theorem carefully. Suppose you have a population, right? And suppose the population variance is sigma square x. That is a population variance, sigma square x. Okay? Then think of the sample variance. Sample variance is what? Summation xi minus x bar square upon n minus 1. Right? You have a sample of size n. So sample variance is, as we have seen, summation xi minus x bar square upon n minus 1. Right? So if you take the sample variance divided by the population variance, right? Okay, fine, and multiply that n minus 1. Right? So if S square is the sample variance, sigma square x is the population variance. If you take the sample variance divided by the population variance and multiply the whole thing by n minus 1, then the resultant follows a chi-square distribution with n minus 1 degrees of freedom. So population variance divided by the sample variance into 1 minus the sample size follows the chi-square distribution with 1 minus the sample size degrees of freedom. What is the degrees of freedom? If you add n independent standard normal squares, you get a chi-square distribution with n degrees of freedom. So the number of chi-squares, the independent chi-squares that you have added together, number of independent standard normal squares that you add together is what is a chi-square, and the degree of freedom is how many of them you have added together, right? This theorem is very important. It is the foundation of why chi-square tests are used. It says that if you take, so if you have a random sample of size n from a population, it doesn't say what population, right? The population variance is sigma square, is a known population variance. Then you calculate the sample variance, which is summation xi minus x bar square upon n. Take the sample variance, divide it by the population variance, and multiply by n minus 1. Then the resultant follows a chi-square distribution with n minus 1 degrees of freedom. Right? So why is that the case? Because you see S square, the sample variance is nothing but summation xi minus x bar square upon n minus 1. Right? Sure? This has to be in the numerator, S square upon sigma square into n minus 1. So if you multiply this by n minus 1, this n minus 1 and n minus 1 will go. So S square into n minus 1 by sigma square is nothing but xi minus x bar square upon sigma square. Correct? Right? Sure? Okay. Now, proof is very simple, okay? I can even also tell it to you intuitively, but let me first go take the proof, right? Very simple. So sample variance is given by xi minus x bar square upon n minus 1. Everybody agrees with this? Yes. Multiply this side by n minus 1, then this n minus 1 will vanish. So S square into n minus summation xi minus x bar square. Mu is the population mean, so inside the bracket let me add and subtract the population mean, should not make a difference. Xi minus mu plus mu minus x bar whole square, right? Sure? This can be rewritten like this. Summation xi minus mu minus x bar minus mu whole square. Just adding and subtracting, right? So this is x bar minus mu plus mu minus x bar. I write is x bar minus mu minus x bar minus mu. No questions? Right? But now, so use the formula a minus b whole square. So this is a square plus b square minus 2ab, this part. I know why you are laughing, but yeah, I will not be political here, right? Okay, okay. A minus 2 into x bar minus mu by sigma, right? Okay. Now, if you add through, then this is the sum of this plus the sum of this minus 2 into the sum of this, right? Sum of this whole thing is sum of this plus sum of this minus. So sum x minus mu square plus x bar minus mu square minus 2 into summation x bar minus mu into xi minus mu. Right? Okay. So now, so xi minus mu square stays as it is. X bar is a constant. It's a sample mean, no? With 3, 4, 5, whatever. Mu is a constant. So x bar minus mu square is also constant. Yeah? So if you sum a constant n times, that is n into that constant. Yeah? So this becomes x bar x minus mu square plus n into x bar minus mu square. Right? Sure? Into minus 2, x bar minus mu is a constant, so it will come out of the summation, and summation xi minus mu. Yeah? Everybody gets this? Sure? Okay. So the next step then is xi minus mu square, this stays as it is, minus 2, x bar minus mu stays as it is, and I open the bracket, so summation xi and mu summed n times, so minus n mu. Right? Okay? So I can now write it like this: xi minus mu square plus x bar minus mu square, right? Okay? Now what is this? If this is, so n is here, this is x bar minus mu into x bar minus mu. Right? Sure, because summation xi minus n mu, if I divide throughout by n inside, right, and add n outside, which is the same thing. If I divide throughout by n and multiply by n outside, then I'll become x bar minus mu into n. Correct? So that becomes minus 2 x bar minus mu into n minus x bar minus mu square. So you get this. Right? Sure? Then, so basically, किधर गया? एकदम खाली आ रहा है. Yeah. Right? So we're here. Clear? So you get basically x bar minus mu square minus 2n x bar minus mu square. So there is n here minus 2n here. So minus 2n plus n is just n. Yeah? So you get summation xi minus mu square minus n x bar minus mu square. Right? Sure? What was this equal to? This whole thing was simply s square into n minus 1. उसको ये सब खोल के किया है ना, s square into n minus 1. Now divide this by sigma square x, you have to divide this also by sigma square x. And then numerator denominator divided by n. So s square, so if you take this, what is this quantity? xi minus mu square is nothing but s square. So basically what you get is here, right? xi minus mu square into divided by sigma square, right? You can put it here, minus x bar minus mu by sigma by root n, because you're dividing everything by sigma now, no? So this quantity, if you divide throughout by sigma x, right? If you divide by sigma x, right, what do you get? xi minus mu sigma x square, right? If you divide this by, so basically s square upon n minus 1 was this, divide by sigma square, right? And then, so basically right hand side and left hand side. So s square upon n minus 1 by sigma square x, right? Minus x bar minus mu by sigma square. And this is nothing but xi minus mu square upon sigma square. This will be xi minus mu square upon sigma square divided by x bar minus mu square. This already there is a sigma square here. There is a n here, right? Okay, there is a root n here. So sigma square will cancel. There will be n here. So we want to put a square outside, I have to put root n inside. Now just think, so the point is just think of dividing everything by sigma square x. Right? Sure? So you will get xi minus mu square minus x bar minus mu by n square. That is what s square upon n minus 1 by sigma square. That is what s square upon n minus 1 by sigma square is, this quantity. Now, listen to this quantity, look at this quantity carefully. There are xi minus mu, right? There are n observations. Mu is the known population mean, right? So xi minus mu upon sigma is a standard normal. How many such standard normals are there? N. They have been squared and added. So the first part must be chi square n, right? The second part is what? What is the mean? What is the variance of x? Right? X bar, what is it? This is x bar minus mu by sigma x, right? Upon root n, right? That is x bar, right? So this second quantity is nothing but an n minus 1 chi-square n minus 1 chi-square 1 degrees of freedom. Yeah? Sure? Correct? So this should have been sigma. There are a lot of typing in this, errors in this book really. So this should have been, basically just think of this, s square upon n minus 1, right? So x minus mu upon, there should have been a sigma x here as well, right? Sigma x here as well, sigma x upon root n, right? Okay, so divide both sides, right? Because if this is s square up into n minus 1, divide by sigma square x, so there will be sigma square x here, sigma square x here, right? N will come in the bracket upon n, right? You can divide both sides by n, so n, and if you put it into square, then sigma by root n that will have to be, right? So the first part is a chi-square n, the second part is only chi-square 1. So chi-square n degrees of freedom minus chi-square 1 degree of freedom is chi-square n minus 1 degrees of freedom. Sure? Right? Is the idea clear? Another way of looking at it is what is s square upon n minus 1 upon sigma square. It is x bar minus xi minus x bar square upon sigma square, right? Or what is it? Xi minus x bar upon sigma the whole square. Right? S square into n minus 1 upon sigma square is nothing but summation xi minus x bar square upon n minus 1 into n minus 1 in the numerator. Denominator only sigma square x. So what do you get? Summation xi minus x bar square in the numerator divided by sigma square, which is nothing but xi minus x bar upon sigma the whole square. Yeah? Actually, you don't even need the rest of this proof, right? All that you can see is, if you're intuitive enough, just look at this. Just look at this, right? Just look at this, right? S square upon n minus 1 is this, xi minus x bar square. Divided by sigma square, this will be divided by sigma square. So you get summation xi minus x bar upon sigma, right? How many such independent deviations from the mean are there? N minus 1, no? If x bar is a sample mean, and there are n observations, then there are only n minus 1 independent x minus x bar by sigma squares. So that will be a sum of n minus 1 independent standard normal squares. So s square into n minus 1 upon sigma square will be a chi-square with n minus 1 degrees of freedom. Right? Sure? Everybody is getting this? Pakka? Okay. Now, why is this useful? इतना सब क्यों किया ऐसा ऐसा करके, right? तो इसका फायदा ये है कि this theorem is a very useful one. Suppose you have a sample, right? Suppose you have a sample of size n, x1, x2, xn, and suppose from a population variance sigma square x, right? S square is the sample variance. So you know that s square into n minus 1 sigma square is a chi-square n minus 1. So immediately you can start testing hypothesis from sigma square x. So for example, there is a sample 12, 10, 11, 9, 4, 15, 13, 7, 19, 15, 13, 14, etc. Right? Suppose your null hypothesis, could this have come from a population variance sigma square x? Null is population variance sigma square x. Alternative is population variance is not equal to sigma square x. Right? If the null hypothesis is actually true, then if you take the sample variance, multiply by n minus 1, and put the hypothetical population variance here, and if this is actually true, then this should follow the chi-square distribution, right? So just like the z distribution, you calculate this, look at the value, if that value lies outside this 1.95, outside that 95% confidence interval, reject the null hypothesis, or fail to reject the null hypothesis, right? Sure? So what is the use of a chi-square distribution? It is used to test null hypothesis about an unknown population variance. The Z test is used to test hypothesis about an unknown population mean when the population variance is known and the data are normally distributed. The chi-square distribution assumption is data is normally distributed and you are testing null hypothesis about an unknown population variance. Yeah? You are testing the null hypothesis about unknown population variance. Right? Sure? Correct? So unknown population variance test करने का होएगा तो I'm not going to take you to the sums anymore because I will do that, right? There are some sums here which you can check out. Right, so do you get the chi-square like this? Right, so you got a lower value and upper value just like a Z distribution. Right, I'm not going to make you do the sums because when you have calculators you don't need to do the sums. You can try out some of the examples here. Then you come to the next important distribution called the F distribution. Right. So what is an F distribution? The F distribution, like the chi-square distribution derived from the standard normal, the F distribution derived from the chi-square. So think of one chi-square distribution that is n degrees of freedom. Think of another chi-square which has m degrees of freedom. So first, divide the first chi-square by its own degrees of freedom. Keep it aside. Divide the second chi-square by its own degrees of freedom. Keep it aside. And then finally divide the first by the second. Divide and rule, right? Okay. You get the F distribution. Right? So take a chi-square distribution, divide it by its own degrees of freedom. So let the degrees of freedom be n. Suppose you have another chi-square distribution which is m degrees of freedom divided by m. Then finally divide the first by the second. So first is a chi-square divided by its own degrees of freedom, n degrees of freedom. In the denominator you have another chi-square divided by its own degrees of freedom, m degrees of freedom. The resultant follows an F distribution with n and m degrees of freedom. So what do you do with the F statistic? It's basically the ratio of two chi-squares divided by their own degrees of freedom. An F statistic is nothing but the ratio of two independent chi-squares divided by their own degrees of freedom. Right? So take the first chi-square, divide by its own degrees of freedom, take the second chi-square, divide by its own degrees of freedom and take a ratio of both, then you get an F distribution. Right? Therefore F is a ratio. And the upper chi-square has say n degrees of freedom, the denominator chi-square has m degrees of freedom, so the F is actually n and m degrees of freedom. Right? Just like as the sample size becomes large, the chi-square distribution also tends towards the normal distribution. Just like the sample size becomes large, the F distribution also tends towards the normal distribution. You should be able to see easily why that's the case in the chi-square. What's the chi-square? It is basically, as you saw, sum of n independent standard normal squares, right? Sure? So by the law of large numbers, these standard normals are going to be normally distributed large sample sizes. So you're going to anyway have the chi-square, right? Sure, is this clear? Okay. Now, so finally what do you use it for? That is the important. Itna kyun karne ka? Right? Okay, now you see the important part. Suppose you have two standard normals, right? So x and y. Right? So first is a sample of size n, the second is a sample of size m. y1, y2, ym. Right? Sure? Okay. Here you look m kiya, but m should be, right? So the variance of the first is xi minus x bar square upon n minus 1. The second sample variance is y minus y bar square upon m minus 1. So what do we have from the data? You have two samples. So you have sample variance from the first data, you have sample variance from the second data. You want to test the null hypothesis that both the samples have come from a population with the same variance. Both of them come from a population with the same variance. Sure? Okay. Then, so the null hypothesis is sigma square x, the population variance of x is the same as the population variance of y. Alternative hypothesis is that they are different. Okay. Now, if the null hypothesis is true, s square x upon s sigma square x, right? Okay. So basically, what you have. So think of what is an F distribution. F distribution is the sum of ratio of two chi-squares divided by their own degrees of freedom. What is the sample variance of the first? Xi minus x bar square upon n minus 1. Right? Okay? Sure? Okay. Divided by, so what is the what is the first chi-square? S square x upon sigma square x into n minus 1 is the first chi-square. Divided by n minus 1, that becomes s square x upon sigma square x. Right? What is the second chi-square? Sigma square y into n minus 1, s square y into n minus 1 by sigma square y, or whatever, m minus 1. Divided by m minus 1, that becomes sigma square y, s square y upon sigma square y. Then you take the ratio of the two. Right? So when you divide, the first chi-square is s square x into n minus 1 divided by sigma square x divided by its own degrees of freedom. What do you get? S square x upon sigma square x. What is the second chi-square? S square y into m minus 1 upon sigma square x divided by its own degrees of freedom m minus 1, so m minus 1 will go. So first क्या बनाया? S square x upon sigma square x. The second is s square y upon sigma square y. What is the F distribution? The ratio of the two. So if you take a ratio of the two, then that resultant, that ratio should be an F distribution with n minus 1 and m minus 1 degrees of freedom. Okay. Now, we can never calculate this, right? Because we don't know the sigma square x, sigma square y. But what is our null hypothesis? They are the same. So this can go, this can go. And only thing remains is s square x by s square y, both of them are known quantities. We can calculate this quantity under the null hypothesis, and if the null hypothesis is indeed true, then the sample variances, the ratio of the two sample variances must follow an F distribution with n minus 1 and m minus 1 degrees of freedom. So again, calculate the critical values, right, and do the test of hypothesis. Yeah?
According to this, we can say x square x equal to sigma square x equal to sigma square y.
That is your null hypothesis, no? Null hypothesis is what? That both of them are the same. So if our null hypothesis is indeed true, then the sample variance of x upon the sample variance of y must follow an F distribution. Because F distribution formula में sigma square x, sigma square y can be cut from the numerator and denominator. If the null hypothesis is true. If the null hypothesis is not true, they cannot be cut like this. So this ratio will not follow the F distribution. So your test is now, test of the pudding is in eating it. Check whether it follows the F distribution or not follow the F distribution. Yeah? Again, you see, what's the null hypothesis? Sigma square x equal to sigma square y. What is s square x? It's our evidence about population variance of x. What is sigma square s square y? It's our evidence about the population variance of the second pump. Our null hypothesis, both of them are the same. In which case this ratio should be 1. If it is really big or really small compared to 1, then we have evidence against the null hypothesis. Yeah? Getting this? So the chi-square test is what? S square into n minus 1 upon sigma square. What are we testing? Where the population, this sample has come from population variance sigma square. sigma square is our hypothesis, S square is our evidence, into n minus 1 is our information. If our null hypothesis is true, then this ratio should be equal to 1, should be close to 1 and only depend upon n minus 1. If our hypothesis is not right, then either S square x is much smaller compared to sigma square or much bigger compared to sigma square. So this ratio should be much smaller than n minus 1 or much bigger than n minus 1. That is how you test the hypothesis. In fact, the mean of a chi-square with n minus 1 degrees of freedom is actually n minus 1. If you have a chi-square distribution n minus 1, its average is n minus 1. S square upon sigma square into n minus 1 is how far our calculated quantity is away from this mean. If S square is very small compared to sigma square, then that ratio will be much smaller than n minus 1. If S square is much bigger compared to sigma square, the ratio will be much bigger than n minus 1. So we expect the value of the chi-square to be n minus 1, but if the actual value is much smaller than n minus 1, much bigger than n minus 1, we say that evidence doesn't seem to fit the hypothesis. Right? And similarly here, we expect the ratio to be 1 under the null hypothesis. Yeah? And if the ratio is much bigger than 1 or much smaller than 1, we reject the null hypothesis. Right? Sure? So that's how you use the, so again, when do you use the F test? When you want to compare two population variances. Use the F test. When do you use the chi-square test? When you want to test null hypothesis about a population variance. There is one population, you have taken a sample of some size, you want to test some hypothesis about the population variance, you will use the chi-square test. When do you use the Z test? When you want to test null hypothesis about an unknown population mean, when the population variance is known, then you use the Z test. Right? Again, Z test, population hypothesis about an unknown population mean. Population variance is known, the Z test. Chi-square test, hypothesis about an unknown population variance. Right? F test, the ratio of two chi-square, we want to test hypothesis about two population variances. Right? अभी क्या बचा? मीन हो गया, वेरियंस हो गया, मीन में एक प्रॉब्लम है. We have only learned how to test hypothesis about the population mean when the population variance is known. A population is not known what to do. Who is going to tell you? ना कोई बता तो नहीं population का variance इतना है. Right? That is where the T test is used. Right? What is a T test? What is a distribution? So if you take a standard normal, right? ऐसे सब झोल-झोल करते हैं हम लोग. Take a standard normal. उसको अलग से रख दो. Take a chi-square. It's like cooking, huh? Okay. Take a standard normal, keep it aside. Right? Take a chi-square, divide it by its own degrees of freedom. Keep it aside. Then take a square root of the chi-square divided by its own degrees of freedom. Then take the standard normal and divide it by the square root. Whatever results follows the T distribution with whatever degrees of freedom in the chi-square. So what is the T distribution? You take a standard normal, keep it there. You take a chi-square, divide it by its degrees of freedom, take a square root, and then divide the standard normal by this square root. The resultant follows a T distribution with whatever degrees of freedom the chi-square has. Idea clear? F distribution क्या होता है? Ratio of two chi-squares divided by their own degrees of freedom. What's a chi-square? Sum of n independent standard normal squares. What's a standard normal? A normally distributed random variable minus its mean divided by standard deviation. That's a standard normal. If you square many and add, then you get this chi-square distribution. If you take two chi-squares, divide each one by their degrees of freedom and then divide one by another, you get an F distribution. If you take a standard normal, if you take a chi-square, divide by its own degrees of freedom, take a square root and put it in the denominator, you get the student's T distribution. Right? ये चार चीज समझ में आ गया broadly. अब इसमें चालाकी क्या है बताता हूँ. ये क्यों करते हैं ऐसा? मेरे को कभी कि why do these guys do all this, right? Why divide these by these, but you now realize how you can test a hypothesis about two population variances. Very simple, elegant idea, na? वैसा भी t distribution में भी students t distribution, right? Okay. So okay. Okay. So think of S square, sample variance, sample of size n, right? S square is summation xi minus x bar square upon n minus 1, correct? X bar is summation xi upon n, right? Okay. Then the theorem says that if you take square root of n x bar minus mu upon the standard deviation from the sample, the resultant will be a t distribution with n minus 1 degrees of freedom. अपन पहले क्या करते थे? We assumed that we thought that sigma was known, population variance. So इधर सिर्फ population variance we used to put, no, instead of S, population standard deviation, and say that this is a student's t, this is a z distribution, right? Now we don't know the population variance. So we are replacing the population standard deviation by an unknown, by the sample standard deviation, and then the theorem is saying that if you do that, then the resultant is actually a student's t distribution, right? So let's see why, right? So let x1, x2, xn be a random sample that is distributed normally with mean mu and variance sigma square. Any questions on this? No. Right? x1, x2, xn is a random sample that is distributed normally with mean mu and variance sigma square x. Right? Okay. Let x bar be this and z is root n x bar minus mu upon sigma x. No doubts about this. Right? So this is a standard normal. Right? Okay. So now this is standard normal. S square into n minus 1 by sigma square is a chi-square. We are supposed to divide it by its own degrees of freedom. So this degrees of freedom are come in the denominator, and then you are supposed to take a square root of this. वो रेसिपी बना है पूरा, राइट? एक स्टैंडर्ड नॉर्मल लिया इधर, पूरा स्टैंडर्ड नॉर्मल है. काय स्क्वायर था एस स्क्वायर इंटू एन माइनस 1 बाय सिग्मा स्क्वायर, आपने काय स्क्वायर बताया, मल्टी डिवाइडेड बाय एन माइनस 1 बिकेम एस स्क्वायर इंटू एन माइनस 1 बाय सिग्मा स्क्वायर इंटू एन माइनस 1, टुक अ स्क्वायर रूट, ठीक है, एंड देन डिवाइडेड वन बाय अनदर, ठीक है. सो दिस इज व्हाट इट इज, राइट? श्योर? इज दिस कंस्ट्रक्शन क्लियर टू एवरीबॉडी? स्टैंडर्ड नॉर्मल ये है, s square into n minus 1 by sigma square is a chi-square with n minus 1 degree of freedom. We are supposed to divide it by n minus 1. So we are divided by n minus 1 here.
It's a population variance, so it's not
Yeah.
distribution.
No, but for what is the definition of chi-square? If you have x1, x2, xn coming from a population with mean mu with variance sigma square, population variance sigma square, then sample variance s square upon sigma square into n minus 1 is a chi-square with n minus 1 degrees of freedom. So all that we have done is s square into n minus 1 by sigma square is a chi-square. We have to divide it by its own degrees of freedom. Divide किया n minus 1. इसका square root we took. Then divided this standard normal by this. Right? Now we are doing something very interesting. होशियार लोग होते हैं. What they have managed to do is put sigma x in the denominator of the fraction and put sigma x in the numerator of the fraction so that they can get rid of both. Basic idea ये है. How to get rid of unknown quantities. Right? So if you actually solve this, what do you get? Root n x bar minus by sigma x, that remains as it is. Right? S square into n minus 1. Right, by n minus 1. This is supposed to follow a t distribution. If you, ये n minus 1 जाएगा, ये n minus 1 जाएगा, then root will go, so s by sigma x, yeah, so this sigma x will go from here and this sigma x will go from here, and what will you get? Summation root n x bar minus mu by s, sample variance, which is the student's t. So it says no matter, even if you don't know what the population variance is, please calculate the sample variance and put it instead of a population variance. But just for God's sake, don't use the standard normal distribution, use the t distribution, and now it's only n minus 1 degrees of freedom because there are only n minus 1 independent deviations. Yeah? Clear? That is how you get student's t distribution. Right? Now I'll quickly show you so is the student's t the same thing as the standard normal? No, there are some differences. Right? I'll show you how those differences look like and why if you have large samples then it doesn't really matter what you use. Right? Both of them become very similar to each other, right? If you have large samples. So it doesn't matter whether you use even if you don't know the population variance, if you use the sample variance, we don't need to use the t tables. You can still use the standard normal as long as the sample size is pretty large. Right? That's what I'm going to show you. And then I'm going to tell you why if the underlying distribution is not normal, then the theory works only if the sample size is large. But you have a small sample size and the underlying and the data are not necessarily normal, what do you use? Then all this distribution theory goes out of the window and we just start looking at the empirical simulations and all that, right? So that's also what we are going to do, right? Okay. So ये समझ में आ गया? Okay. So now look at this, right? I'm all going to do is, okay, I'm going to distribute a Z distribution first, right? Okay, so let X be our norm, right? Say 1 lakh values, yeah? Mean 0, standard deviation is a standard normal, right? Correct? This will generate for me 1 lakh values, right, which are normally distributed, means from a normal distribution with mean 0, standard deviation 1. So standard normal. Y is equal to RT, random number from T distribution. How many do you want? 1 lakh, but I want them to have only 6 degrees of freedom. Right? Sure? And now I'm going to plot for you the two densities. Right? Plot density X, color is equal to red. Sorry, the color has to be outside this. Color, plot density X, color is equal to red, right? And on this I will superimpose the density of Y. Y is the density of the T distribution with 6 degrees of freedom, right? So lines density Y, color is equal to blue. Yeah? Sure? So the blue line is a student's T distribution. The red line is the standard normal, right? Okay. Yeah? So what is the blue line? The student's T distribution with 6 degrees of freedom. First look at this, then you will understand. So first look at the theory and then you can play around with the numbers, right? So the blue line is the student's T distribution. The red line is the standard normal. You see a difference between the two distributions? The student's T distribution has fatter tails, no? Such distributions are called leptokurtic distributions. They have tails which are fatter than the normal distribution, right? So there are some extreme events which are more likely to happen compared to what the normal distribution will predict, then you lose the T distribution, right? Okay. Obviously, it matters here which critical values you use. Because if I use a certain cutoff value, then the area to the left and the right will going to be different from the red lines and the blue lines. Yeah? Sure? Okay. Now, if I change this, right? Let me close this. Okay. If I change this degrees of freedom from 6 to say 20. Yeah? Right? Then they become more closer, no? Yeah? They become more closer. Right? Sure? If I go from 20 to 30, if I go from 20 to 30, they're almost identical, right? And if I go to say 100, right, then see what happens. If I go to say 300, then first cut off this older graph. It's an older graph that I want. Then I have got. They're almost perfectly coinciding, right? So, if you have a small sample size, and if you use the Z distribution instead of the T distribution, you'll go wrong because the two distributions are different. But if your sample size keeps on increasing, at about 30, those two distributions don't seem to make much of a difference, right? Then beyond that, you don't really need the T table. You can still use minus 1.96 plus 1.96. Hello, Yetare?
Oh, sir, Yetare.
Huh. So basically, so 4 distributions we learned today. Standard normal. Tell me, when do you use the standard normal distribution? Quickly. Standard normal distribution, Z distributions are upayog. When do we use it? When we want to take tests of an unknown population mean, when the population variance is known. When do you use the chi-square distribution? When we want to test hypothesis about an unknown population variance. When do you use the F distribution? When you want to compare two population variances. And when do you use the T distribution? When you want to take tests about an unknown population mean, when the population variance is not known. All these theories require the data to be normally distributed if the sample size is small. If the sample size, as the sample size becomes large, all these distributions get closer and closer to the standard normal. So for large sample sizes, all that matters is the standard normal or the Z distribution, right? Okay, otherwise you have to use the TF chi-square Z. These are 4 building blocks of all statistical hypothesis testing. And these ideas will be used in various contexts, right? Sure? Yeah? Clear? So we'll now do some t-tests with R, very simple to take, right? And then I will also try and teach you some, next class we'll see if we don't really, if you want to do a t-test, but the data are small sample and we don't know whether they are normally distributed or, right? Then how do you actually do it, right? And that's how modern statistics goes really. It doesn't anymore depend upon these assumptions of normality and all that, right? Okay, so that's something that will, right? So currently, okay. So now, suppose X is C, these are the values of X. You can use the t-test also to compare two sample means. That's called a pairwise t-test. Okay, so what you're really doing is you're taking one sample, you're taking another. Null hypothesis that they come from the mean with population same mean. So you take null hypothesis x bar 1 minus x bar 2 must be 0. Alternative is x bar, and then you actually just combine the variances. Basic idea is simply again the old t, right? ये आ गया? लिखा सबने? Okay. So all that you have to do is to write t dot test x. What do you get? The value of t is 5.6338. Why is the degree of freedom 10? N minus 1. Okay. The p value is 0.00123. So that's the probability with which you will go wrong if you reject the null hypothesis. Right? What is the null hypothesis here? That the mean default null hypothesis that the mean is equal to 0. The default null hypothesis that the mean is equal to 0. So the default H naught, if you don't specify any null hypothesis, the default H naught is mu is equal to 0. Right? If you want to specify, then you have to say mu is equal to something. We'll come to that, right? Okay. Now, how have the confidence intervals been constructed? Root n, x, we did that, right? Root n, so x bar plus or minus 1.96 sigma by root n, right? In our case, now what will happen? Instead of 1.96, it will use the values for t distribution with 10 degrees of freedom. There will be a 2.5% value, 2.5% value for t distribution here. So that value will be used instead of plus 1.96, minus 1.96. And instead of sigma x, sample standard deviation will be used. Instead of the population standard deviation that we are using in the confidence intervals to calculate the z values, now we'll be using the sample standard deviation, right? And you will get the confidence intervals for t, right? Okay, so if you just say qt, right? Okay, qt and say 0.025, sorry, and how many degrees of freedom? 6 degrees of freedom, minus 2.44, right? So the lower 2.5% cutoff will be minus 2.44 and the upper will be 0.975 on 6 degrees of freedom will be 2.44, right? So if using minus 1.96 plus 1.96, the standard, the confidence intervals will be using minus 2.44 plus 2.44. And these will change with the degrees of freedom. Yeah? So if I take say degrees of freedom equal to 6,000, right? Degrees of freedom are large. It's 1.96. So very close to the normal. Right? But if I just take 6 degrees of freedom, it's going to be a different number. So that says that the standard normal gets closer and closer to the t distribution gets closer and closer to the standard normal as the degrees of freedom increase. It converges really, right? Sure? Clear? TF chi square z पक्का गया? Okay, now इसमें से if you want to take the null, instead of taking test of hypothesis suppose you want to specify a mu, right? So null hypothesis is null 45. Yeah? Then all that you have to go here and say mu is equal to 45. Why is the t-test 0 now? Because sample population mean are 0, right? P value is 1 because you can, you know, if you reject that null hypothesis, the sample population is the same. So if you reject the null hypothesis, you will go wrong 100% of the times. Yeah? And the confidence intervals and all that. Sure? If you want to test the null hypothesis that mu is equal to 40, say 40, what will you do? What part of this will have to change? Mu is equal to 40. Yeah, it's so simple. Right? And now interpret this for me. So will you reject the null hypothesis that mu is equal to 40? No, because the p-value is pretty small, right? And the confidence intervals are 27.20 and 62.79. Yeah? Right? Yeah? Similarly, you can compare two means. Right? You can compare, null hypothesis can be that if you have two samples and if you have to test whether both the samples have come from the same population, then the t-test is what you're going to use. Then it's called a pairwise t-test. So you can have, say, y, right? Y is, say, some number. Yeah? So all that you have to write here is x comma y. Story over. Yeah? So alternative hypothesis, true difference in means is not equal to 0. The null hypothesis, true difference in means equal to 0. So basically variance differences, what it's doing is calculating a total variance of the two. So the variance that we use with the sample variance of the first divided by its degrees of freedom. So basically it's a weighted thing. So sigma square 1 into n1 upon n, right? Sigma square 1 upon n and 1 into plus sigma square to the formula करत होते आणि total. But basic idea is the दोन्हीचा एकत्र घेत होते. दोन्हीचा व्हेरियन्स डिनोमिनेटर मध्ये जातो आणि नल हायपोथेसिस वेदर x1 bar minus x2 bar is equal to 0 or not. You can also take two one-sided tests, right? So if you want to know how to take one-sided tests, you should type help t dot test. Alternative, right? You want to take a two-sided test, less, right? So your null hypothesis could be that mean is equal to 5. Alternative could be mean is less than 5, right? Or greater and all that, right? Sure? Then if you are comparing two pairs, two samples, then whether you want to test whether the variance of the two samples you are assumed to be equal or different and so on. Right, so that's all really. So ये समझा? और तुम्ही रेकॉर्ड करताय ना? मी त्यांना पाठवता येईल आपल्याला आज लगेच ना, ते काय मिस झाले ते. समजा क्या? क्लिअर? तू काय म्हणत होतास? एक्स अँड वाय दोन सॅम्पल असतील तर टी मध्ये फक्त एक्स अँड वाय घालायचं. ते सगळं त्यांना ते लावायला लागेल तिथे परत. हां, डिजिटल तेच आहे. कॅमेरा फक्त बघ. Don't worry folks, we got the recordings recorded, so they'll send you the recordings right away. Okay, so I'm sorry for this internet coming and going, but they'll be sending you the recordings right away for today and yesterday also, last class also, right? So basically, everyone understood how to do the t-tests And what are the situations in which we will be doing the 4 tests, right? Pakka? Yeah? Sure? See, this is a very important thing, okay? So please remember, because you need to know when to use what. And a lot of econometric theory is essentially built on this. Right? For example, regressions, we take an F test. Because what are we trying to do? We calculate the sum of squared errors from a model without any of the independent variables, another with independent variables. And what you do is comparing the variances. Therefore, you use an F test. Right? Okay, so once you understand what these tests are, for what? Like when you do a regression t test, you're really testing a coefficient, you do a t test. You're testing a specific null hypothesis. You're taking the coefficient minus the null hypothesis divided by the standard error of that coefficient, which is nothing but the standard deviation. Right? So all the testing that you will be doing will be based on understanding what we are doing now. Yeah? So as long as you understand that well, सगळ्यांना कळलंय? खरं? काहीतरी सांगतोय तू. आयदर तुम्ही मला फसवताय किंवा स्वतःला फसवताय. दोनपैकी काहीतरी असणार. त्याचे I have sent you that PDF. Read that PDF carefully. Right? Sure? Okay, so can we stop today? Next class we'll do 2 things. One is when we do not know the distribution of the data, and the data not necessarily normal, sample size is small, how to do permutations tests and Monte Carlo t tests. So underlying distributions have to be generated from the data itself rather than using some from theory. And then we will start the linear regression model. Now we are up to it. Now we can understand. We are enough to know what to do. Right? And we'll do the simple and the multiple linear regression just one lecture. It's very easy. Very, very easy really. Sure? आतापर्यंत सगळ्यांना कळलंय? पक्का? हा बघ ना घरी जाऊन असं ऑटोमॅटिक काय? ओके? सो थँक यू फोक्स.